So here we are for the last part of today's lecture, and it concerns divergent sequences. Okay, I will talk about divergent sequences. So we investigated the behavior of convergent sequences and then the behavior of the sequence an equal to n, and we isolated a statement about it that was the following. Fixed an arbitrary number, the sequence lies eventually at the right hand side of such a number, of course, on the real line. Okay, so let us give us some precise definition. So we have definition. So the sequence an is said to be positively divergent if for every k in R there exists an n bar such that whenever n is larger than n bar, an is larger than k. Of course, as in the other definition of convergent sequence with the epsilon, n bar depends on k. That is that here the feature I isolated is exactly the same feature I isolated when speaking. So for every number, eventually the sequence lies at the right hand side of this number. Okay, so there is a specular definition, a symmetric definition for negatively divergent sequences. So the sequence an is said to be negatively divergent again if for every number, regardless of its size, in particular of its negativity, there exists an n bar such that for every n larger than n bar, then an is less than k. Again, n bar depends on k. So symbols that we use we have that whenever an is positively divergent, then we write an goes to plus infinity, and also the limit of an is equal to plus infinity. And when vice versa an is negatively divergent, then we write an goes to minus infinity and limit of an equal to minus infinity. An example, a very simple example that you can work out by yourself is given by the following exercise. So we have that an is equal to n to the power alpha with alpha larger than 0, and then prove that an positively diverges. And I will here do another exercise a bit more complicated, which is the following. Prove that the sequence an equal to 2 to the power n squared plus 1 is positively divergent. So let K in R so we aim at finding n bar such that whenever n is larger than n bar, then an is larger than k. This is just the definition of positively divergent. And so what we have to do is to consider the inequality sequence 2 to the power n squared plus 1 larger than k. And this is like an inequality in the unknown n. And study for which values of n such inequality is satisfied. So we can distinguish several cases. First case we can discuss is the following. The first case is k less or equal than 0, and this is very easy. If k less or equal than 0, the inequality is always satisfied because this is an exponential. The exponential is always strictly positive. So this is the inequality, let me call it asterisk, is satisfied for every natural number n. Okay, so this is very easy. And so this is the first case. The second case, more interesting, is for k positive. So we start from this inequality here, and then we take the logarithm of both members. Why? Because logarithm is a monotonic function, and a monotonic function simply respects the inequalities. So from asterisk we have that log of 2 to the power n squared plus 1 has to be larger than log in the basis 2 has to be larger than the log in basis 2 of k. Why log in the basis 2? This is by monotonicity of logarithm. We have still to study monotonicity, but the fact is that the logarithm is an increasing function. If you already know monotonicity, understand it, otherwise accept it. Okay? The monotonicity makes it possible for the logarithm to respect the inequalities when you take the logarithm of both members. Now, why logarithm in basis 2? Because if you have logarithm in basis 2, here you simply have n squared plus 1 larger than logarithm in the same basis 2 of k, which means n squared larger than logarithm in basis 2 of k minus 1. And here again you can distinguish two cases. And the case is 2a is the case in which this quantity is negative, so which means that k is less than 2. K less or equal to, always larger than 0. We have that n squared is always strictly larger than this guy here. So for every n larger or equal than 1, then n bar is equal to 0, because when n is larger than n bar, the inequality is satisfied. 2b is for k larger than 1, then this inequality can be just translated by using the square root, translated in an inequality into an inequality in n. So here we have n larger than square root of the logarithm in basis 2 of k minus 1. So for instance, one can take n bar equal to the integer part of square root of logarithm in basis 2 minus 1, because now you know that when you take n larger than n bar, so you have at least this integer part plus 1, which is strictly larger than the argument of the integer part, and then you are done. Okay? And so this seems to be very difficult, but at the end it was not so difficult, very standard. Okay, another exercise I want you to study by yourself, and this is quite interesting and quite important, is the following. an equal to minus 1 to the power n times n. So the question is this sequence divergent? So work out this example and then we will discuss. And again, here there is some theorems and some algebras, and this time I will not give you the proofs of that. Okay? And so let me just list the theorems that are quite simple. First is uniqueness. The uniqueness of the limit holds not only for the convergent sequences, but also for divergent sequences. So if an goes to plus infinity, then an does not converge to a finite limit L and does not diverge negatively. Okay? This bar means that the statement is false. Second, permanence of sign says that if an goes to plus infinity, then AN as eventually positive. Third, comparison. AN goes to plus infinity, but Bn is not smaller than AN, then it's like having just one carabiniere, then Bn goes to plus infinity. And as a homework, I can ask you to prove 1, 2, and 3. You have to mimic a bit the previous proofs of the analogous theorems for convergent sequences. Okay. And now we can also extend all the algebra that we proved for convergent sequences, and now we got the extension of the algebra of limits to divergent sequences. And so En goes to L, and Bn goes to plus infinity. First rule, very simple, An plus Bn, so L plus infinity, goes to plus infinity. Second, bit more complicated, An times Bn goes to plus infinity if L is larger than 0, to minus infinity if L is less than 0, and if L equal to 0, this is a delicate case, and so this is to be studied case by case. In the old languages, one said that this is an indeterminacy. I don't like this way of talking. So the idea of indeterminacy is that this is simply not covered by the algebra of limits, but what you have to look at is the algebra of limits. What is not in the algebra of limits has to be worked out separately. So 1 over Bn goes to 0, so one says that 1 over plus infinity goes to 0. And then if An is not a convergent sequence, but it is a negative divergent sequence, so An goes to minus infinity, Bn, as before, goes to plus infinity, then you end up with the fourth rule of this new algebra. An plus Bn, again, is to be studied case by case. while the fifth rule concerns the product of the two sequences AN and BN. AM times BN goes to minus infinity. So plus infinity times minus infinity equals minus infinity. And okay, this is all for divergent and convergent sequences. And now we can start to see something which is a bit more interesting and a bit more delicate for sequences. So to say, we talk about monotone sequences. Okay, monotone sequences is a extremely important topics. And the main message of this chapter, it is not elementary at all, is that monotonicity implies regularity. So let me see how. So first, I give you a definition. What is a monotone sequence? So a real sequence AN is said to be monotonically increasing if you compare an element and its subsequent, then the subsequent is not smaller than the previous one. And this is true for every n. Less or equal, okay? So notice here, also the constant sequence is monotonic, monotonically increasing. And now there is, of course, a symmetric definition for monotonically decreasing sequence. So real sequence AN is said to be monotonically decreasing if every element is not smaller than its subsequence. So a comment that you have to keep in mind is the following. In the definition, there is the sign of less or equal, or larger or equal. So with the equal. Therefore, as a consequence, for instance, the constant sequence is both monotonically increasing and monotonically decreasing. Okay? And so in particular, the definition of monotonically increasing and monotonically decreasing are not mutually excluding. Mm? But however, in many cases, it is useful to use the signs without the equal. So I give you here another definition that says that a real sequence AN is said to be here I have to cancel. Is said to be strictly monotonically increasing if every term is strictly smaller than its subsequent. And again, there is the symmetric definition for strictly monotonically decreasing. Here it is, and here you have AN is strictly larger than AN plus 1. Okay? Of course, strictly monotonically decreasing is a particular case of monotonically increasing. So, another remark, quite stupid, but it's the following, that strictly monotonically, very long words, increasing implies monotonically increasing. Sorry. Of course, the same thing can be said for monotonically decreasing, and vice versa is not true. For instance, constant sequences are monotonically increasing, but not strictly monotonically increasing. This is just a matter of definition, and as examples for what we already know, we have that AN equal 1 over n is strictly monotonically decreasing. AN equal to n is strictly monotonically increasing. And so finally, AN equal to minus 1 over n is neither monotonically increasing nor decreasing. These are just the definitions, and then we will start with the next lecture by saying that every monotonic sequence is regular, where regular means that they have a limit. Okay, so have a nice job and see you tomorrow at the virtual classroom for question time.